I explained to you the difference between electromotoric force, ne? Yes, you made a picture there at the bottom, and the terminal potential difference. And I said those are the two important definitions to know of the first page. The rest is not that important for grade 12, but the rest of the definitions you must find in your exam guidelines, especially the new ones that I handed out yesterday. Okay, now we're just going to revise resistance and Ohm's law. Okay, so Ohm's law said a conductor increases with an increase in temperature, and we spoke about that. We said, okay, there are four things that can influence the resistance of a resistor. That is temperature, the most important one that we will consider the most. There is the thickness of the conductor, there is the length of the conductor, and that is the type of material of the conductor. Okay, but we know if the temperature increases, then the resistance of the conductor also increases. Right, then Ohm's law says the potential difference is directly proportional to the current at a constant temperature. So if you keep that temperature constant, then the rest will remain constant. But if you increase it, if it becomes warmer, then the current will decrease, or the volts might increase, or what. Okay, right. So here on the right hand side we have two graphs. Okay, now in last year's notes we had the bottom graph. Okay, where we had volts versus current. I just want to show you this here that you can also have current versus volts. And now I realize that more often than not they give this graph in the end exam, this type of graph where they compare current with voltage. Yes. Okay, right. So when we compare current with voltage, now both of them are a straight line graph, as you can see, but there's a big difference in the gradient of the two graphs. Now, ma'am, the gradient looks the same. Let's look at their gradients. Okay? Why do we look at the gradient? We always look at the gradient if we get a graph. Especially a straight line graph tells us a lot of information. Okay? So if we look at this first graph, so all of this will be on the first graph. Okay, we will do that on the first graph. If we look at the shape of the graph, we can make a graphical conclusion. The graphical conclusion looks at the shape of the graph. Now this is a straight line graph, or do you call it a linear graph? Straight line, linear, doesn't matter, straight line graph. And with that graph, we can say that the y-axis is directly proportional to the x-axis. So we can basically say that our y-axis, we have the current, is directly proportional to the x-axis, volts. Okay, that is how we read this graph. You always read from right to left, so we can say the y is directly proportional to the x. Okay, right. Now a graphical conclusion, you have to use numbers or formulas. Okay, now what is the formula for a straight line graph? It is y is equal to mx plus c. Now as you can go, it goes straight through the origin. So that c is equal to 0 for this one specifically. Now in the exam, you might get one that is not going through the origin. Okay, then we will hopefully get a chance to look at an example like that, but then you will determine that cutting point where it cuts the y-axis. Okay, in this graph, you have that the y-axis is current. We don't know the gradient just yet, and the x-axis is the volts. Okay, so that is a graphical conclusion that you can make. And from there, you can determine the gradient of the graph. So you can rearrange it to get the gradient is current over volts. Okay, now that looks sort of familiar, but not really. Okay, if we go back in time, then you remember we have R is V over I. Now this is just the inverse of that, omgekeerd. Okay, so basically we can go rewrite this as 1 over m is not 1 over m, sorry, m over 1. M over 1. What's wrong? If I say, Zanelli, I have
I was questioning, isn't it the same thing?
It's exactly the same thing. But what I want to show here, if you say you have 2, or if you say you have 2 over 1, is the same thing. Okay? So what I want to do is, I know that if I flip the right side around, V over I know that is equal to resistance. Okay? But okay, so that is equal to resistance. So if I go back, reverse, then I over V is equal to, nee, wacht, I confuse myself now. That is equal to resistance. Swap them around. That is 1 over R. Yes. Okay. So if we go back to this drawing here, then we can see they did give us the gradient here. They said, be careful for this graph. The gradient is 1 over resistance. So they can give you a graph like this and say, right, please determine the resistance used in this practical. Then you say, oh, resistance is the gradient, laka. Remember, the resistance here is 1 over the gradient. So you must swap them around. Okay, right. Here, if you calculate the gradient here, I'm just going to do it quickly. Gradient is y over x. This y here is volts. This x is current. So here the gradient is just R. So for the one graph, it's 1 over R, and the other one is just R. Okay, so from there we can get Ohm's law from that graph where it says, the definition, the potential difference across the conductor is directly proportional to the current in the conductor at a constant temperature, and we have this formula. Okay, and if we get a resistor that obeys Ohm's law, that it adheres to Ohm's law, then you get a straight line, and we call it an ohmic conductor because it obeys Ohm's law. So here I say, for an ohmic conductor, a conductor that obeys Ohm's law, the graph is a straight line. Okay, then you also get a non-ohmic conductor. So it does not obey Ohm's law, or the ratio is not constant, so it makes a curve like that. So it doesn't obey Ohm's law, the resistance doesn't remain constant, the temperature doesn't remain constant. That is not necessarily a bad thing, like a heater or an oven or a kettle or whatever is a non-ohmic conductor because it heats up. Okay, right. So that is just a revision of Ohm's law. We're going to do a question on that a bit later on. Then just a revision on resistors and different series. So we get a series resistor and parallel resistance. So here I want you to have at least 2 highlighters. If you don't have in front of these highlighters. Okay, so we're going to just look at the different type of circuits, and we're going to look at how does the current and the volts compare. All right, so if we look at the current, okay, so the current, I said last year, is the number of electron men. How many men passes through per second, blah, 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 blah. So here you walk all the men, nowhere can it split up the current. So we can see the current is the same everywhere. Okay? If we look at the volts, now we said the volts there is our energy or our sandwiches or whatever, the energy that we have. We see in this circuit we have 3 periods. So you had life sciences, Afrikaans, and science. physical sciences. So you have to split up your energy into the 3. So you can see here that resistors, in series are potential dividers, energy dividers, volts dividers. So you have to add them together to get the total volts. Okay, and then if we need to get the total resistance, we just add them normally. Okay. So let's look at a small example here. They say calculate the reading on the ammeter in the circuit. So what you do is you take your highlighter, you say there, the little man walks, do. You can see everyone passes through there, everyone passes through there, all there, and everyone passes through the ammeter. So that ammeter measures the total current. Okay. You can see there we have 6 sandwiches, and you need to split up your sandwiches into life sciences, Afrikaans, and science. At the end of the day, that's taking a lot of energy. But you are here. Well done. And you are sort of awake. Yeah? Right. So they asked calculate the reading on the ammeter. We checked, we saw that we wrote down that measures the total current. So we need the total resistance and the total volts. Now that total and total are not formal formulas. Okay, so you don't need to write a total there. I just do it for myself so that I can organize my mind. Okay, the total volts we have at the top there is 6. The total resistance, can I just say 2 plus 4 plus 12? No. Yes, I can, sorry. Yes, I can. Why? Because they are in series with one another. If it's in parallel, then it's a whole different story. Okay, so I can just say 2 plus 4 plus 12, that gives me 18. Okay, you are grade 12 now. You don't need to show how you add the things together. Okay, so now we want the current. If you look at the formula that will be on your data sheet, that is the formula. So remember, you always write it down exactly like they give it to you. Then you substitute values. That's 6 over I. You see the I is at the bottom. No, we don't like it there, so we crisscross. So we have the current is 6 over 18, and that gives you 0.33 amperes. Okay, so it's a refresher on series circuit. Little bells goes off in your head. Way at the back, ne? Yeah. No. All right. The next type of circuit that we have is a parallel circuit. Okay. So if we look at the current here, the little man walks. Everyone passes through there, and then they split up into 1, 2, or 3. So you have a choice between. Do you have a choice between accounting, geography, and tourism? Okay, so you have a choice. Right. Now, you all get a certain amount of energy, sandwiches, before you start the day. Those that choose accounting have that amount of energy, sandwiches. Those that choose tourism have it. Those that choose geography has it. Okay, so just because you take accounting does not mean you get more sandwiches. Everyone gets the same amount of sandwiches. So you'll see I highlight them the same. Okay, it's not there, but I'm just going to ask those that choose accounting, that goes here. Is accounting difficult? Yes. So does the most kids take accounting or the least amount? The least. So why are you laughing?
They're looking at me like, I said no, it's not.
Sure, what's your mark in accounting? Yeah! On fire! Alright. Okay, so we're not asking Zanele. Right, so because it's the most difficult, considered to be the most difficult between all the subjects, the least amount of kids take it. Okay, right. So we can say here the potential difference, the volts, is equal. So it's the same everywhere. But the current splits up. You can choose where you want to go. Okay, so resistors in parallel are current dividers. Now, because you have a choice, because you don't have to take accounting and geography and tourism, you have a choice. We can't just add them together. And that is why we do 1 over R parallel, to make it easier, to make the resistance less. Okay, so let's look at an example like that. Okay, so here we walk. Yellow. Everyone walks with their 6 sandwiches. Then you have a choice. Either you have, what's easier, geography or tourism? Okay, so either you have tourism, or you have a double accounting, or you have geography. Okay, so that's your choice. So there's 3 branches. But your energy, those that choose tourism, they have 6 sandwiches. Those that choose a double accounting have 6 sandwiches, and those that choose geography have 6 sandwiches. Okay, right. Then this ammeter, because the whole current passes through it, it's like register, it measures the total current. Okay, now they ask us, I'm going to just divide my page into 2. They ask us calculate the reading on the ammeter in the circuit. Now the ammeter measures the total current. So for that I need the total volts and I need the total resistance. The total volts is given, that is 6 volts. The total resistance, can I just say 2 plus 6 plus 6 plus 4? No, because it's in parallel. But because the 6 and the 6 are together in series, it is like one long period. Okay, so you can add them together to give you 12 ohm. So that branch is like a 12 ohm resistor. Okay. So I'm going to add them together. I'm going to say 1 over R parallel. Just going to zoom in here. Is 1 over 2 plus 1 over 12 plus 1 over 4. So that gives you 6 plus 1 plus 3 gives you 10. 10 over 12. Now this is a very important step. You must show that now you turn that 1 over R parallel around. To say 12 over 10, and that's 1.2 ohms. How do you check again to see if this is the correct answer? That must be smaller than the smallest one in parallel. Is it smaller than 2? Yes, it is. So you think you're on the right path. Right, so that is 1.2. Okay, so now we go. Resistance is volts over current. Our resistance we calculated as 1.2. Our volts is 6, and we want to calculate the current. The current is underneath. We don't like it there, so we crisscross to get it to the top. And you get I is 6 over 1.2, and you get 5 amperes. Okay, now the next question, at question 2, they ask, calculate the current in each branch. So it means we have 5 learners, and we want to know how many learners chooses tourism, how many chooses accounting, how many chooses business. Business, geography. Okay, right. So there we go. Let's look at the second one first. Okay, now I'm already going to rearrange my formula just to make it easier. So we want to calculate the current is volts over resistance. We said since they are in parallel, and since there's nothing else going on there, that total 6 goes to each branch. So the volts there is 6. The resistance in that branch is 2, so that is 3 amperes. So we see from the 5 learners that's in the school, 3 of the learners go to tourism. Does it make sense? Yes, because the easier it is, the bigger the current. Okay. Then we're going to look at the 12 ohm resistor. Again, we want to calculate the current. The volts is 6, the current, the resistance is 12, so that's 0.5. So only a silly half man with just a head and arms will choose to take a double accounting period. Someone like Zanele, ne? Will say, isn't it nice to do double accounting? Okay, right. Now, without any big calculation, how can I just say, just give a number, a value of what is the current through the 4 ohm resistor? Yes, you're going to say the current through the 4 ohm resistor will be 5 minus, so the total current is 5. There we have 3. There we have 1.5, 0.5. So here we have 1.5. So it's going to be 5 minus 3 minus 0.5, and it gives you 1.5 amperes. Right. Let's just look at another concept that I want to practice. It says there, calculate the reading on the ammeter, blah, blah, blah. Before I do that, I'm going to take out my highlighters and I'm going to consider. So there my little man walks. Do. You get there. Everyone needs to pass English. So that there, the total current passes through it. Then when they get here, they have a choice between math literacy and mathematics. Okay, they will not go through the voltmeter because the voltmeter has a very high resistance. It's impossible to pass through. Then they get together here again and the total current passes through that ammeter. If we look at our sandwiches, then you have 2 things to prepare for the day. You must either go, you must go to English, and then you have a choice, either math or math literacy. Okay? So, but you don't have to do both. So we know that the volts there and the volts there will be the same. The energy that you get when you go to lit or maths is the same. Okay, right. Now, the question there, question 1 is, and I think we're going to divide our page into 3. The first question is, calculate the reading on the ammeter in the circuit. So we have written down there the ammeter measures the total current. So for that, I need the total volts and the total resistance. The total volts they gave me to be 12. The total resistance, can I just say 4 plus 3 plus 6? No, because these two are in parallel. So I must first get their parallel resistance and then add that to the series resistance. Okay, so that's a lot of calculation. So we're going to say 1 over R parallel is 1 over 3 plus 1 over 6. That gives me 3 over 6. And then I must switch them around to give 6 over 3. And that gives me 2 ohms. Does it make sense? Is it correct? Is 2 smaller than 3? Yes, it is. I think I'm on the right path. Right, then that is just the parallel combination. I want to get the total resistance. So for total resistance, I must add that 4, that other series resistance to it, so that I get 6 ohms. So the total resistance is 6. Okay, so now if I want to calculate the current, is volts over resistance. So that is 12 over 6, and I get 2 amperes. Right. Now, in the next question, they ask us, calculate the reading on V1 and V2. Okay, now, since V1 is in series, it looks like it will be the easiest. So I'm first going to say, let's look at V1. Okay. Right. So we need the resistance and we need the current. We saw here that the total current passes through there. Okay, so I have just calculated the total current, that is 2. That voltmeter is over the 4 ohm resistor. So that resistance that I write down there is 4. If I want to calculate the volts, it's current times resistance. So it is 2 times 4, and that gives you 8 volts. So it means of the 12 sandwiches that you had, 8 volts goes there. Now without doing any big calculation, what will be the reading on V2? 4, ne? Because you had 12 sandwiches, you ate 8 already at English. So how much do you have left there? You have 4 left. You say 12 minus 8 gives you 4 volts. Alright, and then the last question, question 3. They ask you calculate the current that is in the 3 and the 6 ohm resistance. Now you could use that whole formula to calculate current, your volts and resistance, blah blah blah. But what I want to practice here is just to go over ratios, because you might be forced to do ratios in the exam. Okay, how do we do ratios again? You say we have a 3 and a 6, so you're going to write down 3 versus 6. Then you're going to add them together, that gives you 9. So you're going to say I have 3 over 9 and I have 6 over 9. Of what? They ask what is the current through each branch. So you're going to say of the total current, and we got the total current to be 2 amperes. So that 2 is what you fill in there, 2 and 2. Okay, now if you do those calculations, you'll get 0.67 and 1.33 amperes and amperes. But you can't leave it there. Okay, because we know, we said a while back, that the bigger the resistance, the more difficult the subject, the smaller the current. They are inversely proportional to one another. Okay, so we can't say the 6 ohm resistor will get the bigger current. That is not true. This here must crisscross. The smaller smaller resistor will get the bigger current, and the bigger resistor will get the smaller current. So how are you going to write that down? You're going to say that is equal to, that is the current through the 6 ohm resistor, and that is the current through the 3 ohm resistor. Okay. Slowly, slowly it comes back to you. Very slowly. Okay. Then here at the bottom of the page, we are going to skip. I rearranged your grade 11 notes. I forgot to delete that from the notes. Okay. Right. Next year, the whole page 6 is a summary of your grade 11 circuits that I added. Why am I yawning? Okay. Of your grade 11 notes. Now, we looked here at the heating effect. Why are we looking at it? Because we just discussed if you have a light bulb, if you have a generator, if you have a motor, if you have a buzzer, or whatever, a bell, then how much energy does it take? Okay, so if you buy light bulbs, your parents say buy the one with the lowest watts, ne? Yeah, to save electricity. Right, so we're going to look here at what energy or electricity we save. So we're going to look at the concept of work and the concept of power. Now we have done this previously this year in the work energy theorem chapter. Okay, so it's sort of fresh in your mind. Yes, sort of. Can you see that if they discuss it here, that they can combine work energy theorem with this chapter? Okay, so they can put in a circuit, and then they can put in a bucket that must be pulled up by the circuit. Okay, so they can ask you, okay, if you have the circuit and there's a little motor in the circuit, what is the power of the motor? And if you have the power of the motor, they can ask you, how long does it take to pull up a bucket of water of this mass up to a height of that with a constant velocity of blah, 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 blah. They have done that in the past. Okay, but we'll get there. Don't cry. Okay, so let's read together now that I've given you a summary of what's going on here. So in the cell, electrons receive potential energy that is converted to kinetic energy. Okay, so in a battery, they have potential energy, it's converted to kinetic energy as they start to move through the circuit. Here they collide with one another, and the kinetic energy, the movement when they collide with each other, is converted into heat energy. Okay, so that is the whole concept of the heating effect. Then we have the work that is can be done. The definition there for work is the amount of work done or energy transferred, and they are measured in joules. Okay, so how much joules does something take or give? And there are formulas to calculate the work that must be done. They're all in your data sheet, and we will discuss or use them a bit later on. Then we have power. What is power? The definition there. Power is the rate at which work is done. And I told you, if you hear the word rate, you must think divided by time. Okay, so here we can see we divided it by time. And there are a few other formulas also to calculate the power with. Okay, just if they ask you in an exam, and they have done that, and we're going to look at a question paper like that, determine the brightness of this light bulb. You must know brightness is linked with power. Okay, the watts is linked with the power. Okay, right. So we're going to look at that in a moment. And then lastly here, they do expect you to know or to be able to calculate the cost of electricity. Now, they hardly ever ask that in grade 12, but we want to make sure that you do know what's going on. So we're going to just do one short example of cost of electricity on this page. Okay, let's say you have a fridge at home, and the fridge is 600 watts. Okay, and your fridge is on for about, let's say you switch it on for 40 minutes. Okay, I just want to use minutes to make it a bit more difficult. Normally a fridge is on for about 18 hours of the day. Now, who puts the fridge off? Isn't it on for 24 hours a day? Why do ma'am say average 16 hours a day?
Doesn't it switch itself?
Yes. Have you ever heard when things are quiet, in the middle of the night you hear, doom, the fridge starts back on. Okay, so like it goes back to a certain temperature, and then a switch goes off and it switches itself on again. Okay, that's why you shouldn't leave the door open. You should leave it closed, because then the temperature is contained, and then it switches itself off more often, and then you save electricity. Okay, anyway, right, so let's say it's on for 40 minutes. 1 hour, blah, 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 blah. And we must go calculate what will it cost us. Okay, now first we want to convert that into units that you buy, and that unit is in kilowatt hour. So we must convert that 600 watts and 40 minutes into kilowatt hour. How do we convert 600 watts into kilowatts? Yes, 12 to 10 to the power -3 divided by 1,000, so that is 0.6 kilowatts. How do we convert minutes into hours? If I say we are here for 60 minutes, how many hours? 1. So what did you do? You divide it by 60. So 40 minutes divided by 60 will give you hours, and that is what? 4 divided by 6. Come. 0.67. 0.67 hours. So if I want to get the kilowatt hour, I must multiply 0.67 by 0.6, and you get 0.4 kilowatt hour. So that is how many units. How much does 1 unit cost? It depends what type of time of the month you buy, né? How much you buy, where you live. Are you legally purchasing units? Huh? Say again?
Do you remember when I said that answer? I think last year I was sitting there.
I can't remember, but do you want to give the answer? Alright. How much is a unit?
It depends, like, at the place, but
I think it's about 2 rand.
I mean, 24, you.
34 is how much?
Yeah, I think
I am about, it's more or less 2 rand. Sometimes a bit more, sometimes a bit less. More or less 2 rand. So let's say if your fridge is on for 40 minutes, not even an hour, how much will it cost you? So you're going to say 0.4 kilowatt an hour times 2 rand, and that will give you 80 cents. Alright, so to do these calculations, I consider it to be general knowledge. Okay, then grade 12s, you have a lot of homework. If you don't answer me, then you don't have a lot of homework. Okay, but I can see you guys are, I'm not going to stop on lessons not done, but I don't want Miss Dednam to shout at me again. So, I'm not going to give you homework, I'm going to do it with you together. Okay. I don't see you tomorrow. We do, I do. Okay. Right. So, we're going to do these 2 questions together and then we're done. Okay. So, they ask you there at question 10. So, at question 11. These questions come from grade 11 question paper. So, we're just still revising grade 11 electricity. Okay, so what you normally do is you go redraw the circuit. Do you need paper? Right, so you redraw the circuit, you write down everything they give you. Then we start. So, okay. There, my little man goes. The whole current passes through there. The whole current passes through there. And it goes back. If I look at my energy, my 12 sandwiches, I must split it up in 2. Some of it goes to the 8 ohm resistor. And some of it goes to the unknown resistor. Nothing goes to the ammeter because the ammeter is just like register. You just say, I'm here, and then you go. Ne? And hopefully the teacher prays for you for the day. Okay, right. Now they say when the switch is closed, the reading on the ammeter is 0.5 amperes. Now, in anything in circuits, the thing that is given at the top of the diagram is already in the diagram, in the picture. The thing that is written at the bottom of the diagram is not in the picture. So don't skip that part. It's an important part that gives you extra information. 11.1, question 11.1.1 they ask, give Ohm's law in words. So here we must say, okay, the current through the conductor is directly proportional to the constant, provided that the temperature remains constant. Now remember, if they ask you, give Ohm's law in words, you can't use symbols. I'm just using symbols to save time, but you must use words. 11.1.2 they ask. Calculate the resistance of resistor X. Okay, now let's check there. What goes through resistance X? The whole current. The total current passes through there. Okay, we want to calculate the resistance of it. We don't know the volts that goes through it or to it, but we do know the total volts is 12. Do you agree with me that because this is a series circuit, I can look at the whole circuit together and say the total resistance will be 8 plus X. Then I have the total current they give to me as 0.5. The total resistance is 8 plus X because it's in series. You can just add them together. And the total volts is 12. Then this looks a lot easier because then I can just say, okay, resistance is volts over current. The resistance is 8 plus X. The volts is 12 and the current is 0.5. 12 divided by 0.5 is 24. Nee? That's I. And then you get X to be 16 ohms. You checked me already. Okay. 5 marks, just like that. It's too easy. Right. Then they ask, consider the diagram at the bottom now. That diagram looks significantly more difficult. Nee? Is it just me? So I'm just going to redraw the diagram for myself. And as I redraw it, I might stress a little bit. But I know if I take out my highlighters, everything will be much easier. No? Yes? Don't you guys get happy if you can take out your highlighter? It takes my mind off stuff. Okay, right. So I say here my little man walks. Do 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 do. When they get there, they have a choice. Oh, you guys are still drawing. Sorry. Okay. Yes.
Can I just ask,
Ammeter.
the position of the ammeter, isn't it gonna, the reading of the ammeter, isn't it gonna be affected by the reading?
If you put it here or there, it's still before it gets back together. So do it. Okay. Right, so when they get there, they have to split up into 2. The men that choose to go through that branch doesn't split up at all. They go through there and then back home. The ones that choose to go through here split up. And they have a choice where they want to go. Then they get back here and back home. Okay, now I have to look at my sandwiches. Now if I look at the big 2 branches, okay, so if I look at this branch compared to this branch, then their volts must be the same. Each branch gets 12 volts, right? If I look at the smaller one, let's look there. Okay, now let's say you choose the 16. So you're going to go there. Here you walk with 12 sandwiches. When you get to the 16, how many sandwiches do you have? 12. Have you used any of it? No. After the 16, you go back home, where you get 12 more. So how many sandwiches do you have afterwards? 0. So there you have 12 sandwiches. Here you have 12 sandwiches. So this is like a deception. Okay, so here we have 12. Here we also have 12 sandwiches. So you can write that down for yourself if you want to. This is 12 volts. This is 12 volts. 12 volts. Can you see why I highlight? Make notes. Do the whole sandwiches thing even though it's really silly. Okay. Now they ask you at question 11.2.1, what is the potential difference over the 4 ohm resistor? There's the 4 ohm resistor. We just determined it to be 12 volts. That is why they ask it, so that you must go look at it because it's important for a bit later on. Then 11.2.2 they ask, calculate the reading on the ammeter. Can you see it counts 5 marks? Normally 5 marks means 2 calculations. Okay, where's that reading? There. What does the ammeter read? That ammeter reads the current of these 2 together. Okay, so I'm just going to label my branches for myself. I'm going to make this branch 1 and this whole thing branch 2. So it's important, easier for me to focus. So the ammeter reads the current of the second branch. So for that, I need the volts of the second branch and the resistance of the second branch. The volts of the second branch, I've already determined it to be 12 volts. So those two gets 12 volts. The resistance of that branch, can I just say it's 20? No, they're in parallel. So I must do that 1 over R parallel business. 1 over R parallel is 1 over 16 plus 1 over 4. That gives me 5 over 16. Then I must remember to swap them around. It's 16 over 5. And that gives me 3.2 ohms. Okay. How do I check to see if I'm correct? Is 3.2 smaller than 4? Yes, it is. Okay, so now I know that resistance is 3.2. So I can go calculate the current is volts over resistance. It's 12 divided by 3.2 and you get 3.9 is 3 bly oor 3 gedeel deur 2. How much is it? 3.75 amperes. Okay, I'm just going to say, how did I do this? They ask, what is the reading on that? I ask myself, what does the ammeter measure there? It measures the current that was split up between the two. So I'm going to look at these two as one thing. Okay, I know their volts is 12 volts. And I know I can add the resistors together to get their one thing resistance. Okay, so that is what I did there. Is that enough for 5 marks? Yes. It's 2 calculations. Okay, sharp. Then the next one, 11.2.3. They ask, calculate the energy that is used or it goes to waste in 2 minutes in the 12 ohm resistor. So they want the energy. We measure energy in joules. What is it what they want? What is that symbol for energy? Watts, ne? Right? They say the time must be 2 minutes. Do we like it in minutes? No, we want it in seconds. So we times 60. That gives you 120. And they say we must look at the 12 ohm resistor. Now, if you look at your formulas, then you have work is volts times current times time, or current squared times resistance times time, or volts squared times time over resistance. Those are the formulas that you can use. For the 12 ohm resistor, there, I have the volts. No. That 12 volts, does it all the 12 volts go to the 12 ohm resistor? No. If you go with your 12 sandwiches here, you must use some of it at the 12 and some of it at the 18. So that 12 needs to split up. So we don't have the volts for the 12 ohm resistor. We don't have the current for the 12 ohm resistor. We have the current going there, but we don't have the current going there. Okay, so let's check here. What I do have is I have the resistance. So I have a resistance, I have resistance, I have time, I have time. I don't have the volts, I don't have the current. So the question counts 5 marks. 5 marks normally means 2 calculations. Okay, so it makes sense that I have to go calculate first the current or first the volts. Okay, I'm definitely not going to do both. So I'm not going to use the first equation. Okay. Mary, which one do you want to calculate, the current or the volts? The volts. Okay, how do you want to calculate the volts? How do you want to calculate the current? How? Okay, not the bell, but the bell is going to ring in 2 minutes. You can calculate the volts using ratios if you want to. You can say 12 versus 8. And you can say there's 12 ohms. Where will it go? Okay. Or you can say, I know the resistance together here is 20 ohms. I know the volts is 12. And I can go calculate the current. Okay. So anyone will be possible to do it. You must just make up your mind what you want to do. So if we say we're going to calculate the current, will be volts over resistance. The volts is 12 and the resistance together is 20 because they're in series in that branch. So you get your 6 divided by 10 is 0.6. Okay? Okay, then we can go use that second formula. The current is 0.6 squared. The resistance is 12. And the time we said is 120 seconds. And if you calculate that, you get... And the unit? Joules. Good. Okay, so can you see these questions with joules and watts and whatever? It will not be difficult. There's not a trick. There's just a bit extra work to do. Okay, right. Now, I can see you guys are gone. I've lost you completely. Okay, what I want you to please do for homework, I know, is question 10 on the next page. Only do until 10.1.4. Not that last part. That last part I'll do together with you in class. 10.1.4. Please. So 10.1.1 until 10.1.4. Okay. Chop. Thank you.